Our last integral on this review is somewhat reminiscent, I hope you're going to be able to see, to what we saw with inverse secant. And it doesn't look quite exactly like what we saw in our notes the other day. But remember, what we saw in our notes was if you had 1 over u times the square root of u squared minus a squared du, that would be 1 over a inverse secant of u over a plus c. Now, of course, as we're looking here, there are quite a few things that don't seem to quite fit. The 4, I think most kids would say looks pretty decent and looks the way that most kids would like to see it. They could say that's a minus 2 squared here. Bottom line is, though, you could look at this as radical 5x squared as well. That's really what you're going to have to do in this problem. You always want to look at your inside of the radical, and actually with inverse tangent where you don't have a radical and you've got your two terms down below, you want to see them as squared terms. So you could even take a square root of that term to see where you're going. Why? Well, right now you have a very good hint that your u would be radical 5x. Du would just be a radical 5 dx, meaning dx would be a du over radical 5. So what gets kids a little bit nervous here, understandably, is the fact that, as you begin to work this out, the u part is the easy part, of course. The dx, you get your du all over radical 5. Again, inverse secant is that problem where things don't seem to be quite right. We're so used to having u substitutions where things are canceling out. And right now I have an integral with an x term that has not canceled out. Now, of course, what we can do is go back to that substitution statement and solve for x and say x is really u over radical 5. And if we look at it that way, then we can come back to this problem. So I'm going to do that real quickly, rewriting this. This would be u over radical 5. And then, of course, we've got this radical u squared minus 2 squared, and then we've got our du all over radical 5. Now, it's at this point where, a lot of times kids will look right here and say, bring the radical 5 up on top, and you certainly could. Or you could also notice that this is really like a radical 5 all over 1, and, this radical 5 would cancel this radical 5. You could see it more easily, perhaps, if you bump it up to that numerator, and then it's pretty evident. But once you've made that substitution, I hope it's very obvious what's about to happen. Let's rewrite the problem. This is now just a u and a radical u squared minus, and here's r2 squared. Right now, this is going to look exactly like what we began our review with, where we said, hey, as we had that lesson on inverse trig, we are looking for this pattern right here. And very clearly now it is an inverse secant graph. So we're going to say it's 1 over a, so that's 1 over 2. And we'll have inverse secant of u over a, so that's u over 2 plus a constant. But again, writing this out algebraically, our u is actually radical 5x. So we've got this radical 5x all over 2 inside of secant. And that's our final answer. As we look at our very last problem on this review sheet, we learned L'Hopital's rule just recently. If we plugged 0 into the top, we'd have tangent of 0, which is 0. Down below, the natural log of 1 is also a 0. So I could use L'Hopital's rule. We could definitely see where we're going with that. Derivative of tangent of 2x is secant squared of 2x with the chain rule multiplied by the derivative of 2x, which is a 2. Down below, the derivative of natural log of 1 plus x is 1 over 1 plus x. You could most certainly simplify this, but what I want to point out to you is that if I let x approach 0, this whole circle denominator, 1 over 1 plus 0, that's getting awfully close to just a 1. We'll have a 2 up here. Secant squared of 0. Well, as you let 2x, let x go to 0, you've got secant squared of 0, but the cosine of 0 is 1. So the reciprocal secant value is going to be a 1 also. Square it, you still get a 1. Final answer then is a 2.